So thanks everyone. So I'm Florian Angeletti. Sometimes people also call me Octacron for unknown reason. So I spend most of my time currently working on the OCaml compiler. A little bit of error message, type system, tooling integration, and release management when I find the time. So there has been an ongoing effort to refactor and document the type checker and type pattern matching compiler inside the OCaml compiler since mostly 5 years ago. And why is that an ongoing effort? Well, the OCaml compiler is mostly by definition the oldest OCaml project that exists in the world. So, which means that it is a 30 years old open source project. So the first commit in the repository is a commit by Xavier Leroy, which saying, well, we are switching to the bootstrap version of the OCaml compiler. Let's hope everything will go all right. And because which is also mean that the compiler is a little bit conservative in its use of new features. Because when you are implementing the new features, and if you start using the new features when the implementation of the new features is broken, you get yourself in a quite painful trap. But can take some time to get away from. If you want to ask me more stories and more stories about that, don't hesitate. And the reason that there is an ongoing refactorization is that we have quite a few authors. So counting from OCaml 4, we have more than 350 contributors. So some of them are quite old contributors, dating back from the first day, but there's still a new flux of incoming authors, and also authors that stop contributing to the compiler. So refactoring code, which is 20 years old, and the author is not really available anymore, it takes some time to be certain that you're doing things correct. And what can we do as an OCaml compiler to be certain that we are doing refactorization in the right way? Well, we have types. And I love types because wide engineering types give you the way to make the right code and the natural code to write, which also means that the weird code, which is doing weird things, and you probably should be refactored at some point, looks weird, which is a good point, because it makes the code more readable. It's also data type are also a good way to document what is going on, but documentation. And if you are doing your job right, maybe the next contributor will be able to refactor your code 10 years later. At least I hope so. So for instance, which kind of refactorization are we working on? Well, there is a little bit of Unicode support in OCaml 5.3, which means that, for instance, nowadays I can define a constructor with accent. That works, but not really something that we are promoting for working developer. It's something that we think, at least I think it's quite important for pedagogical purpose, because when a student is learning OCaml, maybe it's not nice to try to teach him English at the same time. And yes, teaching language can be quite a heated discussion sometimes. But when we started to try to do that, the first concern was, well, but wait, which model we associate to a file called et.ml? Because there is 4 different ways to write these strings in Unicode. Which one do you choose? And more importantly, how do we make sure that we make the same choice everywhere in the compiler? Well, the answer is create a new type that describes how we pair files with the module names and be certain that we are doing this computation exactly once for every file. And doing this, you create a new data type. You have some very natural function, but say, well, if I have some information about a file, I can compute the semi-file artifact easily, but you also see some weird function appears. For instance, we have a companion semi function that is telling you, well, if you give me an artifact, I expect to be able to find a semi file right next to the artifact, which means that which is kind of weird because we are writing in the answering in the compiler, oh, we distribute files, which is not right. But that's what the compiler was doing, and maybe we will refactor it later. So types are nice, and if I love types, but let's say that the OCaml as a language also love types, because, well, we have algebraic data type, finds, we have records, yes, they're very nice, but we also have tuple, or polymorphic variants, or objects. Yes, we have objects, don't forget this. But we also have extensive variants, or first-class model, and GADTs. So quite a bit of a show of data type that you can use. And part of this talk is trying to describe when we are using them in the compiler, how helpful they are to do refactoring or not. So let's start with the easy side, the product types. So the first product type is a very simple tuple, which are nice. You don't need to declare them. You cannot do recursion. What do I mean by we cannot do recursion? Well, if you try to write this function, the compiler tells you, well, no, this tuple, the second part has the same type that the type of the word tuple. And it throws you away most of the time. So no recursion, which are right, and they are everywhere. But part of the problem with tuples is that they tend to aggregate and grow in size. And you know, I'm getting old, or maybe because I'm theoretical physicist, but counting higher than 1, 2, 3 is hard. And when I have tuple with more than 5 type parameters, it's getting quite hard to remember in which order they appear. So tuples are nice, but the free for all nature of them sometimes make refactoring difficult, which is why recorders are most of the time much better once you start to have big type or big bundle of data, because you can name the field, you can have recursion, and most importantly, you have label spinning. Label spinning is one of these very small features that if you look at the language definition, you say, that's so nice, is that very useful? And then when you start to use the language, you realize that, no, that's one of the most important features of the language, because it rewards the lazy, it rewards the programmer that uses the same name everywhere in the code base, which means that the lazy programmers will use this name because you are rewarding him, and that is very important, to be certain that people agree on the names of things, and naming things is very important. And rewarding people that use consistent names, yes, that helps a lot when refactoring. There's also with update, which also give you a way to add new fields without refactoring all your code, which is nice. So that was pretty controversial. So let's go to more controversial topics. Object, because yes, we have objects in OCaml, and we have class also. If you look at the property, well, you can define your object types with a definition. You only need class definition when you would want to share code through inheritance. Object also give you subtyping. And objects are used in the OCaml compiler, only in the native backend, because the implementation of object is quite complicated, and we want to be certain that we still have at least the bytecode compiler if something goes wrong in the object implementation. So we don't have object in the bytecode compiler? Well, it depends a lot of what you call object, because, so what is an example of object in the native compiler, which is instruction selection from architecture. So mostly it's saying that depending on, selecting instruction depending on the architecture. But so we also have records that looks like that. And those records are object with an explicit this argument. So we have objects in many situations because they're very useful when you want to do open recursion and shortcut between mappers or functions that traverse the trees, and you just want to update a little part at a time. So to finish the product type side, we also have first-class modules, which are a way to bridge the value and module levels that give you subtyping. And if you get your subtyping, give you type inside the record, which also means that it's another way to implement an object system that people tend to overuse. But I think there is a single use of first-class module in the compiler, and it is to switch the implementation of one module between the Windows version or the Unix version, which is a nice way because it means that you have this function that is evaluated at runtime and which allow you to switch a module implementation. So we have done with the product type side. So let's speak about variants, or the many variants that we have in OCaml. So we have the standard algebraic data type, where you need to declare them in advance. Recursion is quite easy, and you can find everywhere. Then we have polymorphic variants. First quick look, you can think that it's just a way to avoid doing definition, because well, I can declare my iter function in the same way than before, just without any kind of declaration. But then you look at the type, you try to read it, and you say, maybe I'm paying the complexity elsewhere. Because, yes, so recursive function can be quite complex to read, and if you use them as just a local variant, everything is fine. But if you start to use them across many modules, at some point you write a code like this, and you have an error message that tells you, well, something went wrong. Where is the error? Oh, there is a he missing. I have a node without E in the definition of map. So, and that errors can happen 200 or 300 modules later, that's the one where you define the function. So that's not so nice. So which means that when you have principal use of polymorphic variants, you need to annotate every use of the polymorphic variant. So we are not so much a shortcut in this kind of use, but they can be very useful to implement complicated recursion scheme. So which means that if you have a tree with many different variants, so for instance, one in the pattern machine compiler, little bit quite, is that better? Okay. So in the pattern machine compiler, so there is our pattern that are one of the most complicated parts of the compiler, and we try to emulate them as early as possible. And to do that, well, it's useful to use polymorphic variant to be able to define a function that would operate on the OR pattern, eliminate them, and then you can define the rest of the function that would operate on the pattern that don't contain OR clause at the top level. And that's a very common pattern because it means it allows you to define small transformation that will remove or add a few constructors at a time without needing to define explicitly all the algebraic data type with one more constructor, or adding two constructors, removing one, and changing the type of argument of another. So, but for this, it's very useful because we are letting the compiler compute type for you, which is nice. So, a short point on extensible variables. So extensible variables are this kind of variables where you can first declare that there is a extensible type, and then you can add constructor. Which means that at the same time you need to declare the type, and you lose the advantage of knowing all the constructor. So it may look like you are losing all the advantage of the normal variant and the polymorphic variant one. But it can be in fact quite nice if you want to implement a plugin-like architecture. So where we have this extensible data entry point that you define in the library, and you add hook in your library to consume this entry point, and it's the consumer that will add this new data constructor and define what is the semantics. And in the case of the constructor, the most used one is the first extensive variant type, which is the type of exception. So in order to have nice error message, you can register the fact that you can register handler for exception, try to catch the exception, and try to look at all your exception handler to find if there is one which gives you a nice error message. And so the exception is the user adjustable entry point. The hook is this register of error function, and which means that you can define the errors at different points without strong coupling, which works well in this case. So last but not least, there is generalized abstract data types. So I like to introduce them in three different ways. So one of the first use cases of generalized abstract data type is to discard type information. So for instance, when I define this type ref and value, I'm saying that under the constructor R, I have a reference and a value that could be put inside the reference. And that's it. Which means that when I have a value of this constructor, I just know that I have this reference and this value that can be matched. And what I can do, I can put the value inside the reference, or I can put the value inside the reference, inside the value, and that's it. And so if you look at the function, the code is pretty natural. So here basically you are defining a function that will set a set of reference to a certain value, and then switch back to the previous value of the function. But it also means that you can have a reference that contain different types, but then in the same list, and because you only kept the needed information, so the fact that you add a reference and a value that can fit in the reference, you can put the different references in the same list. So it's a nice way to lose type information when you started with too much type information. And that is very important with GADT, because GADT are also a way to add way more type information inside your data type. So a good, easy way to see the need for GADT is that sometimes you have types that kind of belong to the same family. For instance, the float type and the int type, when you are doing addition, you can define a function that add float and a function that add int, and morally they're the same. So with classic algebraic data type, you could define a type name that contain both a float constructor and an int constructor, and then you can have a single addition function. But you are left with this weird case where you have int on the left side and float on the right hand side, and you don't know to handle them. You didn't want to handle them. And A good solution for that are the GADTs. So GADTs, we are you to group together type that belong to the same family while still keeping information, type level information about the different branch. So here I'm saying that, wait, my type name is, it takes a flat argument and return a flat name, but it's a mistake here. And same thing for the int type, which means that my addition function works on the same alphanym types, which means that I can only add int to int and flat to flat. And which means that I can define my add function, the single add function that I wanted, without handling all the cases that didn't make sense. And yes, and that's a good use case for GADT. Is as another way is to say it is to do the subtractive way and look at, for instance, at a normal variant type. So let's consider a small pattern matching. So I want to be able to match on arrays of variable or on exception and on OR pattern. So a quite natural definition would be to go to the algebraic data type, and then I would have an entry for variable, an entry for array, an entry for exception, an entry for OR clause. But then, with this definition, I'm allowing this. So an array that contains, that traces an exception, that doesn't make sense. And I don't know, and I could add assert false in every branch of my code that try to handle this case. But that would be quite a lot of assert false. So GADT are a solution to say, well, the truth is that I have two kinds of pattern. I have computation pattern that can appear when I'm matching on the result of a computation, and I have value pattern that correspond to all the things that match on values. And then I can encode the rule that a variable is a value pattern, an exception is a computation pattern, and an OR clause takes a pattern of any kind and a pattern of the same kind and returns a pattern of the same kind. And then I don't need to handle, and then the case of exception under exception becomes impossible. But, well, the problem with GADT is the complexity cost. So when you look at format fprintf, it's quite a useful function. You can try to pick inside the content of the format implementation and looks at, but this is not a string. If it was a string, I couldn't change the number of arguments of this function. So this is probably a GADT. And you can ask the top level to show you the GADT by adding a type information. You probably want to open OCaml Internet Format Basic to have a type that is quite readable. And then you end up with saying the real GADTs behind the format string. But the implementation of the format module sometimes looks like that. So you have a format, a type constructor with 12 parameters. And let me point you something. So this is the features that require these 12 parameters. Does anybody has ever used it? Does anybody even know what is this feature? Well, this is the feature that allows you to define, to print like that. So you can say format.printf, and I will take as my first argument another format string, which will take two integers as argument, and then I will print using that format string. So, which means that for this word expression, print something like this, which is not very useful. Like say is 90% of the complexity of the implementation of format strings. So yeah, it's a bit of a problem with GADTs. If you want to prove more things, you end up mostly trying to prove things in the OCaml type system. But the point to keep in mind is that OCaml is not rock. So it's not a proof assistant or dependent type system. So you can prove a lot of things, ask me anytime to see what kind of things you can prove, but you probably don't want to prove anything. Or unless you want to prove only the property that you really, really care about at the cost of the code, your code complexity. So let's conclude. So type engineering is maybe it's a question of personal expression, because it can be a great way to express your intent, to prove property about your code, to try to not overdo it, and also a great way to refactor very old code because people will be sure that all the property are preserved, and you will not need to try to pick inside the head of the people that written the code 10 years ago to try to have them explain which invariant is really necessary here. Do you still remember? So, yeah. I think my conclusion is the first on my side. I love type, and I think it's a great way to express oneself. Thank you.
Thank you. Thank you. That was interesting. Any questions?
Thank you for your very nice talk. I have a question about the format string. Can you go back to the slide? Yes, that one.
Which one?
So I suspect you have asked other audiences whether they have ever used such a statement. And is there any user of that feature? And if the answer is no, what would it need to actually remove support for that from the OCaml compiler?
Yes.
Because I noted, I look quite a lot at binary sizes of binaries produced by the OCaml compiler. And there, the standard library, especially the caml format internal or caml internal format, is a very huge part that contributes also a lot of binary code to the compiler. That is float printing, I suspect. But this feature, for example, I mean, what would it need to actually remove it?
Yeah, so indeed, it's a very important point. So let me add a very important note. Please don't start to use this feature because you have seen it on my talk. Really, please don't do that. Because yes, I hope at some point that we will be able to remove it, probably by trying to deprecate it and 10 years later remove it. Yes, problem with being on the standard library. At the same time, so there are some effort to try to remove the dependency of camel internal format basic, the dependency of stdlib of these internal modules, which is here due to, I think, one type definition and the format concatenation operation. So I hope that much earlier that we will be able to remove this feature, we'll be able to move these concatenation operators in another modules to free the stdlib from the format influence. And another thing that I'm looking at is to have a completely different implementation of format, probably using PPX at first, and that would implement, let's say, a much lighter API.
Okay.
Thank you for your talk. This was extremely interesting. There's one kind of typing feature that's not used in the compiler, I think, which is effects, if I'm not mistaken, currently. Do you think there's going to be an addition to the standard library sometime soon, or to the compiler itself that might, sort of touch on effects? And the kind of complementary side to this question is, are there any other typing things or type-related things that are not used in the compiler at the moment?
So for effects, probably at some point we'll have some effects in the standard libraries. Hopefully, when people agree on concurrency primitive, because it probably would be nice to centralize the definition of some effects, possibly. Inside the compiler, effects are part of the complicated implementation features that we probably don't want to use soon because the feature could be broken in difficult way to predict, and we don't want features with complicated implementation in the path to the bytecode. At the same time, I have some case in mind where you could have a fork of the compiler with effects for instance, reading CMI file, which could be quite nice to have. So, for instance, to have perfectly accurate computation of dependencies.
Thank you for the talk. You mentioned replacing tuples by records for which are much more handy. Do you have an opinion about labeled tuples, which are kind of in between with a declaration?
Yes, I had them on my slide at some point, but then I decided to be cautious and to not add on my slides features that are not implemented. But yes, I think they are probably a good intermediary step, because sometimes you want to have internal records that are used across one function, maybe 2 or 3, and defining one type that would be used in only 3 functions is a bit heavy-handed. So named tools sounds like a good idea to have an intermediary step. But then it's also adding one more data type to the data type draw